Hello, hello, and I've got another Fiddler puzzle for you this week. This week's I think is quite a bit harder than last week. In fact, I'm not 100% sure I even have the right answer. I'm fairly sure that for the normal question I have the right answer. Extra credit, I'm less sure on. Uh, but anyway, I'll go through my thoughts on the puzzle, and if you find an error I made, please let me know. And this week's Fiddler involves a different type of puzzle called Slitherlink. And I'm not actually that familiar with Slitherlink. I've done it a little bit, certainly no expert. But the basic idea of Slitherlink is I have these dots on a grid, and I'm going to end up drawing a loop, a simple closed loop between the dots, only moving orthogonally among the dots, and try to get there. So for example, I might have a loop that looks like this, where I'm connecting all these different dots to each other, and that would be a valid Slitherlink loop. And the question that the Fiddler asks is, how many valid Slitherlink loops are there in this particular grid? So the reason I really like this puzzle is I think it frames the question in a way that is actually not so easy to get, but that you can reframe the question in an easier way that will really help you think about it. So for me, I can think you could go through and try to count and try to think through, well, how many paths can this take and how many ways can you go around and do something like that to try to figure out how many loops there are. But I think there's a much easier way to frame this, and that's to think instead of about the loops of, let's think about instead the shapes inside the loops that get made. So one thing to note here is that for a loop to be valid, it can't cross itself. So you can't end up with a shape like this because it crosses itself. And even if you said, well, is there a way I could do this with not crossing itself? I could start here, maybe loop around. And then when I get to that point that looks like an intersection, I could go down instead of straight across. And then I'm not really crossing myself, right? No, doesn't matter. Can't touch at corners, can't cross itself. This is not a valid Slitherlink loop. So back to the idea. So I'm going to really quickly introduce the idea of polyominoes in case you haven't heard of it. So polyominoes are basically 2D shapes made up of a bunch of equal sized squares. So you're probably, if you're familiar with this at all, you might be familiar with dominoes, right? So dominoes are just two squares kind of melted together, right, into a little rectangle. And you might also be familiar with Tetris, right? So tetrominoes are the shapes that get put down in Tetris, and they're just all the shapes you can make from four squares kind of pasted together on the edges. And so polyominoes is just the general term for this when there's any number of squares that you might use. So why is this going to be relevant? Well, let's think about the Slitherlink loop again, right? So in order for the Slitherlink loop to be valid, well, I could start thinking about, I could move across here and kind of go up and over. And the only thing I'm not allowed to do is go back to the loop before I get back to where I started. So instead of going back here, I need to go down and around. And I could go straight across, but maybe I go down instead and just keep going until I get back to where I started. Now, if I do that, right, I'm forming a simple closed loop, and kind of by definition, all the squares inside the loop will have to be touching because I never did something where I cut off the shape from itself. All those squares are going to be touching. So I'm going to end up with a polyomino if I do this, right? And so another way of framing the question is, it's not quite the same, and we'll get to it later about why it's not quite the same. But basically the question is, how many polyominoes, kind of unique polyominoes, can I fit in this grid, including kind of the different places I can put them in this grid? So instead of thinking of this like the loop, we're going to think of it in terms of polyominoes. And so I'm going to think of these red squares as kind of being somewhere in the grid. And so I might have a shape like this, where I have this T polyomino, and I could draw a loop around it. But the polyomino, in this case a pentomino, is what I'm going to be thinking about. Now note here, the green squares would not form a valid Slitherlink loop because I need two different loops to make that work. And similarly, I can't have something like this where the red squares go off at an angle. I essentially have two distinct shapes here. So that's just not going to work. It needs to just be a basic polyomino. So first, let's think about where I only have one square. I think it's called I don't know if it's a monomino or a monomino. Monomino. Yeah. So anyway, how many places can I put this? Where I can put it here, I can move it over, I can move it to the next one. I mean, I'm not going to go through each one. There are 9 ways I can do this, right? 9 places I can put this single square and have it work. What about dominoes? Now, dominoes, I have to be a little bit careful, right? I can take this particular shape and I can move it, right? There's 6 different places I can put this, but I can also rotate it, right? And if I rotate that domino, there are 6 more different places I can put it. And so if I want to be careful and add these all up, I can think, well, there's 6 different ways I can put each orientation, and there are 2 different orientations. That's 12 different places I can put this domino. That's going to result in 12 different valid loops. What about trominos? Well, now I have to be even more careful because in addition to having, I can stack the 3 like this, and that's one orientation that could have 3 different placements. I can rotate it. That also has 3 different placements. But I also have like a different tromino, like a fundamentally different tromino, which is this bent tromino. And here I can put this in 4 different places on the grid, right? But I can also rotate it, right? And when I rotate it, that one has 4 different places I can put it. So does this one, and so does that one, right? So altogether, there are 3 places to put each straight tromino and 2 orientations for each of those placements. That's 6. For the bent trominos, there are 4 orientations and 4 placements for each orientation. Add that all together and end up with 22 different ways to do the trominos. Now you can probably guess that as we get into larger numbers of squares here, the number of shapes is going to get a little bit out of control. So we can get to tetrominoes, that's the Tetris pieces here. What about the square? There's 4 places that I can put the square, right? So I'm not going to think much about that. Instead, I want to think about this skew shape because this shape is pretty interesting. So this skew tetromino, it is interesting because I can rotate it, I can move it around, but I can also reflect it, and that's going to result in a fundamentally different shape. So before I get to that, let's just think about this. Well, I can take this and I can rotate it, but even just thinking about rotating it, there's 2 different ways I could think about that, right? I could rotate it down to here, or instead I could have rotated it and have it ended up on the top. And so you'd have to make sure that when you're thinking through all these different shapes, that you're careful about not double counting particular rotations and translations, because rotations and translations in this context can get a little dicey. They can start to look the same. But the other important thing, let's go back to this reflection idea, is that this shape and this shape, these are fundamentally different. There's no way to get from one to the other using rotations or movement, which I'm going to keep calling translations, right? Another way to think about this is I have actually I have a 5-year-old son, and he has a game where it basically is these rubber 3D versions of polyominoes that you put in a little board and try to fill the board up with all your little shapes. And he loves this game, but he still has a hard time with shapes that can that have this property, like the skew tetromino, where sometimes to fit it into a particular slot, you've got to turn it upside down, right? Or in the case of this 2D plane, you've got to reflect it, right? It's really a fundamentally different shape. You can't just twist it around to get it where you want to go. And so for here, with the skew tetromino, the way I'm going to end up thinking about this is there are 2 different, fundamentally different shapes, right? These 2 different skews, 2 different reflections. And for each one, I can rotate it 4 different places. And so that's going to end up with 8 total possible placements. And you may think, well, can't I shift it down? But think about this. If I take this and I rotate it twice along, the way I'm thinking about rotating it is taking the entire 3x3 box and rotating it 180 degrees or 90 degrees. If I do that rotation twice, it's the same thing as just shifting it, right? So this looks the same as this, just shifted up by 1 or down by 1. And that's the same thing as doing 2 rotations. So another way of thinking about this is this shape has 180 degree rotational symmetry. And so you just have to be careful not to double count those movements and those translations. Now contrast this to the T shape, which does not have the property that it needs to be reflected, right? I can do every single possible orientation and placement of the shape without ever reflecting it, right? I can take it here, because if I reflect it, so in this case I'm reflecting it vertically, right? If I reflect it horizontally, nothing happens. I can think about reflecting it, but I can equivalently think of that reflection as just rotating it by 180 degrees about the center of the 3x3 box. So I don't ever actually I don't need to reflect that ever. And if you go through each shape, the square has 4 possible placements. The skew and the T have 8 each. Again, for kind of different reasons, but in each case, there's essentially one way you'd be double counting things if you did all possible rotations, reflections, and translations. Whereas the L shape, you get all 16. And the way I think about that 16 number is for each orientation, there are 2 placements, and there are 8 orientations because you're going to get 2 reflections and 4 rotations. Or equivalently, you could think about that as 2 reflections, 2 rotations, and 2 translations. I mean, it doesn't really matter which way you think about it. You're going to get 8 either way. Sorry, but your double, you need it. Sorry, you need all 4 because to get to 16, you then need to do the 2 placements. But anyway, there's no double counting with the L's. There's no way to go from one shape to another using reflection and rotation. In other words, if you reflect it, you are at 4 fundamentally new rotations, which is untrue of the skew shape. So we'll get 36 in total with the tetrominoes. For pentominoes, now we have to be a little bit careful because for the pentominoes, well, I guess I had to be careful with the tetrominoes too. So we might have noticed that there's no line tetromino here, and that's just because it doesn't fit in a 3x3 box. Pentominoes, there are many more, right? So a third of these pentominoes just don't fit in the box. And we can go through each one and think about how many ways there are to do it. Like, so for the F, there are 8 ways to do it. Because once you pick an orientation, you can't move it. There's only one place it can go in the box, but there are 8 different orientations. I think about that as 4 rotations and 2 reflections. But you could think about it as 4 different reflections and 2 90-degree rotations. That's really equivalent. For P, you get to 16 because it has the same properties of F. It has the same kind of degrees of symmetry, which is to say 0. But it only takes up a 2x3 box. So for each orientation, it can go in 2 different places. So there are 16 there. T and Z actually only have 4 ways to do it. So, and I think these are fairly similar, but maybe not. So for every given orientation, there's only one place that can go in the box, but how many orientations are there? So for T, the way I think about it is reflecting and rotation do the same thing. So I'm just going to do the 4 rotations. With Z, I think about it a little differently because now I need to reflect it to get all 4. I can't, if I just rotate it, if I do 2 90-degree rotations or 180-degree rotation, I end up back where I started. So I need to reflect it to get the other 2 possibilities. But either way, I end up with 4 orientations. U also has 4 orientations, but because it only takes up a 2x3 box like P, you get 8 possibilities because for each orientation, I can put it in 2 different spots. So U, you might think it's like P, but because there's a position of symmetry, you only get to 8 possibilities. Now V and W, when I first did this, for some reason I figured this out for V, but not for W, even though they're really exactly the same. There's only 4 ways to do this for V and W for each. So why is that? Because at first glance, it doesn't really seem like they have, in this picture, they're kind of diagonal. But if you put them in a orientation that would align with a Slitherlink grid, there's neither vertical nor horizontal symmetry. And there's not rotational symmetry. So why is it the case that there's only 4 possibilities for each? And the reason is because even though there's not any of those things individually, there is this kind of reflection, rotation, combination symmetry that exists. And the reason it exists, looking at this picture, you can see it more obviously, is because it does have kind of this diagonal symmetry, right? So if I tilt these the way they're tilted in the picture, I do get vertical symmetry, or I don't know if you'd call it vertical or horizontal symmetry. Basically, if you reflect it across a vertical line, you'll end up with the same shape. And so because of that, it's not as obvious when you put it in the Slitherlink grid, but if you reflect it and then rotate it 180 degrees, you'll end up with the exact same shape. So you have to be careful not to double count that as well. So there are 4 each for V and W. And X, there's only one way to put that in the grid, right? The center's got to go in the center. And it's going to go out, up, down, left, and right from there. It's the only way to put X in there. So you only get 1 from X. And so altogether, we get 49. Now, for hexamonos, I'm not too proud to admit that the first thing I did was went to Wikipedia to get the picture of all the possible hexamonos. Right, I'm not as familiar with these shapes, and so I wanted to make sure that I didn't exclude any of the possible shapes. And I'm not going to go through each one. You basically do the same thing, look for the ways that the orientations are going to overlap. And now, but what's easier about the hexamonos is the rectangle is the only one where you have to worry about the number of places it can go. Everything else, once you get an orientation, there's only one way to put it in the grid. Now, you're going to end up with 48 spots. Now, for heptamonos, that's 7 squares. I'm going to shift gears. I don't think it makes sense anymore to count. Maybe this didn't make sense for hexamonos either, but I think it kind of did still. Once you get to 7, first of all, some of the heptamonos are going to be reasonable heptamonos, but not valid Slitherlink loops. We'll talk about that in a second. But more importantly, this is the point where I think it makes sense to start thinking about excluding squares rather than including squares. So when we're building things from hexamonos, we're fundamentally saying, what are the 6 squares we're going to put in? Now from here, I want to instead start thinking about what are the 2 squares I'm going to take out. And now to do this exercise, I want to introduce a combinatorics idea, which is very, very useful for puzzles like this, which is the combination or choose. And so if I have these 9, I want to take 2 away, right? So in this case, I took away the top left and the top middle. But that's not the only 2 I could have chosen, right? I could basically choose any 2. And the question is, how many ways can I do that? So there's the combination or a choose function in combinatorics is exactly going to answer that question. And so in general, if I have some integer n, or really positive integer n, or I guess 0 works too, so a natural number n, and I want to choose some natural number k of them, how many ways are there to do that? So I'll try to the formula is just you take the n number, you take the factorial, and factorial just means take that number and multiply it by each descending number. So if I had 4 factorial, that'd be 4 times 3 times 2 times 1. So you take that, divide that by k factorial, and divide that by the difference factorial. So if I want to do, for example, 5 choose 3, that would be 5 factorial. Again, 5 times 4 times 3 times 2 times 1. Divide that by 3 factorial, 3 times 2 times 1. And divide that by 2 factorial, 2 times 1. Now, I want to do, again, what is the intuition behind this formula? And now this is the way the formula is usually written because I think it's the easiest way to memorize. But I think it's actually a little bit easier if you do n factorial divided by n minus k factorial and then divide that by k factorial. So let's get into what these factorials are doing. So that factorial is telling me how many ways I can order a certain number of things. So if I have 3 objects, say, the number of ways to order that is 3 factorial. Why is that true? The way I think about it is this. I want to order 3 different objects. So how many ways can I do that? Well, first I'm going to think about how many ways can I choose the first object? Well, there are 3 things that I could choose from. I'm going to pick one. There are 3 ways to do that. Now, how many ways are there? Once I've picked the first one, how many ways are there to pick the second? Well, there are only 2 things left to choose from. So there are 2 ways left to choose that second object. And then for the third object, there's actually only 1 way to choose it because there's only 1 thing left. So the total number of ways to order those 3 different objects is 3. The number of ways I could choose the first object, times 2, the number of ways I could choose the second object, times 1, the number of ways I can choose that third object. So that's 3 factorial. Now, what if I didn't want to pick all 3? So let's get a bigger number so it doesn't work. What if I had 5 objects and I wanted to order 3 of them? How would I do that? Well, that would just be 5 times 4 times 3 using the exact same logic. Now, one way to represent that would be, well, I could say 5 times 4 times 3. But to make it kind of tractable from a formula sense, I could just say, well, it's 5 factorial, and I'm going to get rid of that 2 times 1 part. I'm going to get rid of those 2 last things I didn't order. So I'm going to divide that by 2 factorial, which is essentially n minus k factorial in the generic sense. So if I wanted to figure out how many ways I can order k objects, it would be n factorial divided by n minus k factorial. So what is that extra divided by k factorial doing in there? That's saying, well, every time I order them, I'm assuming a specific order, right? I'm saying order these k objects, order these 2 objects. But if order doesn't matter, then I'm double counting, right? So if I go back to this picture, I'm choosing 2 to take away, but it doesn't matter which one I take away first and which one I take away second. All that matters is which 2 got taken away. The order does not matter at all. So I'm double counting if I say, get rid of the top left and then the top middle. And then another way to do it is get rid of the top middle and the top left. So how many ways am I double counting? Well, it's the same thing as saying how many ways can I order those two objects? And that is k factorial, or 2 factorial in the case of 2. So that's where this formula comes from. So if I want to do 9 choose 2, that's 9 factorial over 2 factorial, 7 factorial, which is 36. Now, another nice thing, which better be true, is that it's kind of symmetric. And what I mean by symmetric in this case is that if I want to take 9 and choose 2 of them, I can do that in exactly as many ways as I can take 9 and choose 7 of them. Now, this is not true if I'm ordering those things, but if I'm just choosing them, it's the same. And hopefully that makes some intuitive sense, because if I have 9 things and I'm choosing 7 to keep, that's exactly analogous to asking how many ways can I take away 2 of them. Those are the same question. Taking away 2 and keeping 7 are exactly the same question. So it better be true that the math works out that it's the same no matter which way I do it. And that's true here, because whether I divide by 2 factorial or 7 factorial first doesn't matter. So I get 36 ways, but this is not the final answer, because some of these 36 ways are not valid Slitherlink loops. So I'm going to try to uncount from that 36 how many ways there are to end up with an invalid Slitherlink loop. So what would end up with an invalid Slitherlink loop? As far as I can tell, there are 2 different ways. Right? I can get rid of that middle square in one of the corners. Now, this is a valid heptamino, but it's not a valid Slitherlink loop because the corners of the heptamino touch each other, right, in kind of the second by second dot. So that doesn't work. And there are 4 ways to do that, because it doesn't matter which corner I take away. I'm going to end up with the same problem. The other problem I can run into is if I take away 2 of the edges and cut off a square from the rest of the group. So now this is not a heptamino at all, right? It's a hexamino and a monomino. So that doesn't work either. And there are, again, 4 ways to do that, right? Essentially, you can just rotate this picture 4 times and end up with the 4 different ways to do that. So in the end, I have 36. I take away those 2 possible problems with 4 each, and I get 28 heptaminos. From here, I promise it gets easier. Octominoes, there's only one way this doesn't work. If I take away any of the other 8 squares, I end up with a valid loop. But if I take away the middle one, I end up with kind of having to draw 2 loops, which again is not valid. It's got to be a single loop. So again, this is a valid octomino, but not a valid Slitherlink loop. So I only end up with 8 possible valid Slitherlink loops. And then I also have to add in one more, is it nonomino or nonomino? Yeah, nonomino. So that is one more thing I have to add. If I add everything together, I think I end up with 213. So that is I think the answer to the main Fiddler. Again, if I'm wrong, please let me know. I'd love to know what I did wrong here. Now for the extra credit, this is much harder. How many not valid loops are there, but valid puzzles are there? So I haven't even really gotten into the puzzles because it wasn't really necessary for this. But what is a puzzle? And just as a note, which will be important in a second, a valid puzzle should get you to a unique solution, meaning it gets you to exactly one possible valid Slitherlink loop that satisfies the clues. So let's think about this shape here, right? And instead of this tetramino rather, I'm going to replace it with the loop, and then think about, well, what is a puzzle that could arise from this loop? Well, the way the puzzle works is I'm going to put a number in the squares between the dots, and that number will tell me how many lines there are connecting dots surrounding it. So in this particular shape, I could put any of these numbers in as valid clues to point toward this shape. So right, the top left corner has 3 lines adjacent to that center square. The middle left has 2, right? The very middle has 3, and so on and so forth. Now, I don't need all of these numbers to generate this shape, but for the purposes of to show what I'm going to do here, it's going to be useful to think about, for a given shape, what does the complete clue grid look like? And I'm going to be perfectly honest, the way I got to a number here is using code, right? I counted them by code. I don't know how you did it otherwise, but I suspect there is a way, because Fiddler is not known for doing puzzles that require any type of coding. You can usually do it, the counting, might be a little tedious, but it seems like it could be done in a reasonable amount of time. Whereas the way I did this, there's not a reasonable amount of time this could be counted in. So I'm open to the idea that there is a way to do this without coding. I couldn't figure it out though. So if you figure it out, please let me know. Very interested to know what the valid way is. But I'm going to talk about how I did this through coding. And I will post my code. It's certainly not the most efficient code in the world, and it's done in R because I'm a statistician and not a coder. So don't at me. But the way I went through it is this is the basic algorithm I thought through. So we figured out these 213 valid loops, right? And each of those valid loops has a complete clue grid. And so for each of those 213 valid loops, I populated the clue grid that would arise from that loop, the completed clue grid. Now that is not the number of puzzles for a couple reasons. The most important reason it's not the number of puzzles is I don't need to include all of the clues, right? I can exclude some clues and that will still be a valid puzzle. And so the question is, well, how many clues can I get rid of and still end up at a unique solution? And the way I ended up counting it was basically I thought about these 9 different squares and I said, well, okay, each of these squares can basically be between the numbers 0 to 3, or it can be missing. And so that's really 5 possibilities, right? 0, 1, 2, 3 is 4 possibilities, and then the missing is a 5th possibility. And so I looped through all 5 to the 9 possibilities. So basically, for each of the 9 squares, was it 0, 1, 2, 3, or missing that clue? And then for that particular possible clue grid, I said, is it a valid clue grid? Now, if it results in a unique loop, that is a valid grid. And so basically what I did is I compared it to the complete grid and saw what was the which of those 213 shapes, which of the given clues could result in that shape. So basically, the way I did this algorithmically is to say, well, okay, for the clues that we're not missing, for which of the complete clue grids did I have complete overlap? And hopefully that number is 1. If that number is not 1, then it's an invalid puzzle. So in other words, what do you mean by is that number 1? Well, that number is 0. That means there are no valid Slitherlink loops that would be resulted from that clue. So that's not a valid set of clues. If that number is more than 1, that means for the given clues, there are more than 1 possible Slitherlink loops that I could draw from it. So that's also not a valid grid, right? So that's the way I went about solving this, is taking all of these 5 to the 9 possible clue grids and seeing which ones, just by pure overlap. I didn't build a Slitherlink solver or anything like that to do it. I just did from the completed clue grids which ones had unique overlap. And if it did, it was a valid clue. Now, if the possibility space were bigger, and I still want to do this from a coding perspective, so say it's were a 5 by 5 instead of a 3 by 3, then I think it probably would have made sense to build a solver. But here, because it's so small, I think it's actually faster to not go through the solving and just do the comparisons. So you may have noticed that actually I didn't include 4 as a possibility, but 4 would result in a possible loop, right? So I could have a 4 here and just draw a square, and then everything else would have to have no more lines except for that square. But I didn't do that in the code because I did figure out there is a way to do that part at least analytically, and which is just counting how many ways to do this with monomonoes. That's enough. Okay. So if I have a valid monomino loop, what I'm going to note is, well, I definitely need to have a 4 somewhere, right? That 4 is going to identify where that monomino loop is. But everything else from that point is just defined, right? There's either a 0 or a 1 clue in all the rest of the grids, depending on where that 4 is. And it doesn't matter whether that clue is there or not. Once that 4 is there, that uniquely identifies a monomino grid. Everything else is just, you can have it or not, it really doesn't matter. So the question is, how many ways are there to do that, right? So each clue is basically on or off. And so I have 8 other possible boxes to put clues in. There might be a clue there, there might not be a clue there. Either way, it's a valid puzzle. So for each possible valid monomino loop, there are 2 to the 8 ways to clue it, right? You have to have the 4, and then the other 8 digits might be there or might not be there. And so the total number of monomino puzzles is 9 times 2 to the 8, or 2304. So, before I get to my final answer, I want to talk about a couple things I did to improve the efficiency of the code a little bit. I really didn't spend a lot of time doing code efficiency stuff, but there were a couple things that were interesting to point out, and so I'm gonna point them out here before I get to the number I got. And also, I want to think about a possible alternative way this could be done, again through coding, but I think it probably would have been faster if I'd done it this way. The first thing is to note is that some loops just definitely can't happen. They're definitely not going to be clued in a valid way. So let me give you an example of what I mean by that. So let's take this. This is a perfectly valid Slitherlink loop that I counted as part of that 213. But there is no way to clue this uniquely, right? So what is the unique grid, or what is the, not unique, what is the clue grid that this would make arise? It's basically a 0 in the middle and 2 everywhere else. And you might be thinking, uh-oh, that looks like a very symmetric clue grid for a not so symmetric shape. And if you had that thought, congratulations, you figured out why this doesn't work, right? Because I can rotate this shape and I get the exact same clue grid, right? The exact same clue grid happens. So there's no way to clue this either of those shapes because the clue grid is exactly equal, right? There's no unique identifier here. So you can't do it. And so I just exclude it from the code. And so what I was technically doing was not, counting the number of possible ways because I did exclude this, but it results in the same thing. So, and that, when I started thinking about that led me to a kind of faster way this might work, which is instead of searching through all the possible clues, instead what I would do is take all of the grids. So I have those 213 grids and the complete clue grids and kind of look for unique fingerprints of a sort, right? So look for ways that I could arrange a set of clues that would uniquely identify that compared to everything else. So that's another way you could have algorithmically approached this. Now, there are a couple problems I can foresee running into. Again, I didn't code this up. I'm not sure that it would be faster than what I did. My guess is it would be faster, but I don't know that for sure. But I think you could look for these fingerprints. Now, a couple problems. Right, so the fingerprints we're looking for is like that 4. Once you see a 4, that's going to be a unique identifier, and you could then just count the number of ways that you could add extraneous clues. Right, now the problem is going to be, for a lot of these, they're going to have to be quite big, right? You're not going to, except for the monomino, you're not going to get away with a single number or even 2 numbers or 3 numbers. You're going to need many numbers to get that unique fingerprint. And for a particular given loop, there may be more than one possible way to clue it. So as an example, if I have a straight tetramino, the clues in that tetramino would be 3, 2, 3. That's going to close the loop. And so one way to clue it might be to have 3, 2, 3, and then, I might be able to do it like that. And I think that would, well, that even by itself wouldn't. I would need a 0 somewhere else to show that it doesn't end up in like a pentamino or something like that. Because 3, 2, 3 by itself is not going to be unique. So I could probably do 3, 2, 3 and a 0 on the side would probably be enough to do it. But which 0 is it, right? It could be any of the 3 zeros, or I could probably do it with some combination of 2 of the adjacent clues, right? Some of the ones next to it might also work. I haven't thought too carefully about what it is, but the point is there are multiple ways that I could clue that validly using different sections of the grid. And so I'd have to count each of those unique ones differently. But once I did that, then for each of those unique fingerprints, I could say, well, how many clues did I not include in the fingerprint? 2 to that number is how many ways that I could create a valid puzzle there. So that's another alternative way that I think would be faster from a coding perspective. It didn't take, it took a couple minutes to run. So, it wasn't too bad on my machine, but I think this probably would be like a more interesting and kind of thoughtful way to do it. But anyway, in terms of the number, I got 40,476 once I included all this coding and the monominoes. Is that right? I'm not really sure. You know, even just as I was doing this video, I found errors that I had made in the code. So um, it's very possible some are still there. It's possible that I'm, making some conceptual errors. And either way, I want you to let me know if I did anything wrong. So looking forward to your replies. But anyway, that's it for this fiddler. I really enjoyed thinking about it, even though I'm not 100% sure I got there. But thanks for listening. Hope you had a fun time thinking about it. All right. See you next week.